Right, thanks, Dan. Thank you. Okay, so as Dan said, we're heading towards higher order logic. In the text that we're following, Monicity and McLean, in these sections, they don't actually use the definition of a topos that we have been looking at so far. They use this other notion of an elementary topoi, which actually turns out to be the same thing as a topos. The reason why is because when we're looking at higher order logic, we want to talk about a power set operator of some form, gaining intuition from the topos of set there. This obviously can be done from the original definition of the topos that we gave because they are equivalent to the one that I'm going to give, but it's easier to do so from this definition that I'll be presenting. So essentially what my talk today is about is it's going to be given the definition of an elementary topos, and I'm going to be proving that this is equivalent to the topos as defined so far in the seminar. Okay, cool. Now, in the proof of that, there's going to be a lot of discussion about morphisms into a sub-object classifier, which can be thought of as predicates. Again, thinking in the topos of set, that's exactly what a predicate is. And so before I give the proof of equivalence of these two definitions, it's going to be natural for me to talk about predicates in arbitrary topoi, and so I'm going to have a small discussion about that as well. So there are two aims for the talk today, which is predicates in topoi and the equivalence of the two definitions. Okay, now before I get started in all of that, there's a few notions from topos theory that were mentioned earlier in the seminar that I'm going to be using quite heavily, and these were brought up in James's first two talks down here. And so I just wanted to quickly recall a few things so that we have them fresh in our mind for the talk. So first off, let's recall what a sub-object classifier is. Now, if a category C has got a terminal object, then I can ask for it to have a sub-object classifier, which is an object omega, along with a monomorphism, which we call the true morphism, coming out of the terminal object into the sub-object, into omega, which is such that if I have any monomorphism from x to y, then there is a unique phi from y into omega, which makes this diagram into a pullback diagram. That's what a sub-object is. Okay, in such a setting, or in the setting when a category C admits all finite limits, it will be the case that this category admits a sub-object classifier if and only if there exists an object omega, which is such that for all x in my category C, there is a natural in x bijection between the sub-objects of x and the homomorphisms, and the hom set x into omega. Okay, great. Now, let's also recall what it means to have an exponential. So a category C, which admits all binary products, we look at a particular object x and we say that an exponential for the object x is a collection of objects written z to the power of x, which is ranging over all objects in my category, along with a collection of morphisms which is also ranging over all my objects in the category. These are our evaluation maps, which are universal in the sense that if I have any f from x cross y into z, there exists a unique g such that that diagram commutes. Okay, great. And then lastly, let's recall the definition of a topos that was given in the seminar. A topos is a category E, which is Cartesian closed, admits all finite limits, and also has a sub-object classifier. Okay, cool. That's all preamble. That's all stuff that has been spoken about so far. So now let's get into new content. I'll start by giving the definition of an elementary topos. Okay. An elementary topos E is a category which admits the following. First, I'm going to ask for a terminal object. Which I'll be denoting by the number 1. I also want all pullbacks I want a sub-object classifier okay, and then there's this last condition. I'm going to ask for a collection of objects which is ranging over all my objects in my elementary topos, which is such that so for all objects in my topos, I have the following bijection. And I'm going to ask for this to be natural in Y. Okay, that's the definition of an elementary topos. Indeed, this is equivalent to asking for a topos.
So, just remind me, Cartesian closed, is that got something to do with having exponentials?
Yeah. So Cartesian closed, we have a terminal object, all exponentials, and binary products. Okay, just want to flag something really quickly because this caused me a little bit of confusion. I actually haven't asked for an adjoint functor here. It looks very much like it, but it's actually not. Simplest way to see it is I'm not asking to range over all omega here. So it's not actually a right adjoint. It will end up being one, but a priori it's not. Okay, I want to flag a little bit of notation and terminology that I'll be using. So in the setting of an elementary topos, if I'm given some morphism in here, then its corresponding morphism from y to omega to the e is going to be called the transpose, and I'll denote it by this. So I'll say the corresponding element. Is the transpose and is written as this like angle bracket or corners on phi, which is standard notation in the setting where we do have a adjunction. Okay, cool. There's an explicit map for the inverse transpose. So commonly we do just say transpose for both. It's going to get a little bit confusing when I'm doing proofs later on, so I'm going to make sure that I'm consistent with this, talking about transpose and inverse transpose, so we know which one that I'm moving between. Okay, we have an explicit map for the inverse transpose, so we can go from so if you give me psi, I send this to, so the identity on a product with psi and then I evaluate on E. Okay, and then this is also highlighting some notation that I'll be using. So the evaluation of E is going from E cross omega to the E into omega is the inverse transpose of the identity map on omega to the E, well, for which there isn't a explicit map. Yep.
That must be something I'm misunderstanding. The omegas that are appearing without the superscript E, where are they coming from that?
Yeah.
The object?
That's my sub-object. So, and then the sub-object also needs to have this monic, which is the true map, and I'm going to be using that as well.
Actually see from that natural isomorphism that omega to the 1 must be omega. So
Yeah.
the omega is actually back there.
Was that? Yes, this is the one. All right, cool. Okay, so now let's move on to the second part of my talk, which is on predicates. Okay, so as a really easy warm-up example, if we think about, so if I take an elementary topos, okay, and then I take any object in it, then what I can do is, I know that I'm in an elementary topos, so I have a terminal object, so I can definitely go from E into 1. And then I also have a sub-object classifier, so this is then going into omega. And this is a monomorphism. So if we think for intuition's sakes about the topos set for 1 second, then this is just sending 1 to 1. And so this is just collapsing everything into the Singleton set. So this map overall is just evaluating to 1 for all values of E. So going back to the world of an arbitrary topos, this can be thought of as, I'm going to write true for all E. Right? And then whenever I'm referring to this map, I'm going to refer to it as true with a little subscript E. So this is the map true, and then this is the terminal map, and so I only need to specify E to tell you what this map is. So that's my notation there. Okay, very basic introduction.
So the subscript is that kind of, it's true for all E in the category.
Yeah, he sort of means for all little e in E.
Oh, okay.
It's the predicate property. In other words, every element would be 1.
I didn't want to talk about elements of
He's
E.
trying to say around several things there.
Right.
Yeah. Yeah, indeed I am. Okay. And that's only going to get worse, so. Yes, it's only going to get better. Okay, so what's the next one? Let's talk about membership. So, in fact, evaluation maps of the form of E. What am I doing? To omega. Okay, this can be thought of as evaluation. Now, in the setting of an elementary topoi, these are the only evaluation maps that we have. Okay, well, at the moment it's all that we have. But I just wanted to say of this form, because the same intuition holds for a topos, of course. Okay, whatever. That's just, these maps can be thought of as evaluation. Why? Hmm?
I'm not sure what it argument.
Oh, I don't know what on earth I've written that for. I've done that. I've only done it. No, like, yeah, evaluation. Okay, that's why I wrote it. Membership. Evaluation maps of the form. Yeah, okay, cool. Sorry, thank you. Okay, cool. Why? The reason why, well, it's not immediate. Let me give you two pieces of information first, and then I'm going to use those two pieces of information to convince you that this can be thought of as membership. So the first piece of information is, okay, how many ways do we have of thinking about sub-objects, right? If I have a sub-object classifier, then I can look at the sub-objects of X. Do I still have it written up? No, I don't. Well, let me write it. Okay, let me give away the answer. There's actually three ways. Because due to my sub-object classifier, I know that I have this bijection. But then because of my fourth condition in an elementary topos, I also have this one. E cross 1 is isomorphic to E. Cool, and these go like this. So if I have some monomorphism, so again, this is actually me just flagging some notation. This is, again, thinking in set. It's literally the characteristic map for S, which is where this gets sent. And so that inspires the notation in the general topos, like that. Okay, and this one I'm not going to have special notation for. So this literally is the adjoint, which I already mentioned earlier. Okay, cool, but these are three different ways of thinking about sub-objects. Also, a morphism E from 1, our terminal object, into E can be thought of as picking an element out of E. Okay, so maybe you don't like all these intuitions, but what I could say instead is in the topos set, it literally is this. So this is justified. Okay, cool. Now that I have this, let's try and understand why we get membership here. Well, let's think about the following. Say I had a predicate, which was just some morphism into omega. Okay, and then say I picked some element out of E. Then the following diagram commutes. And the diagram is this. So, I end in omega, and I have E, so this is where I have my predicate. Okay? And then I have my element that I'm picking out of it. Okay, good. Now, I have an isomorphism here between 1 and just 1 cross 1. And I have another isomorphism here between E cross 1 and 1. Okay, so think about this diagram for a second. I can make this E cross, okay, I apologize for my notation, the identity map on the terminal object, 2 different usages of 1 there, and that's going to make this diagram commute. This isomorphism is projection, and by definition of that product map, that definitely commutes. Okay, and then here I can go into E cross omega to the E, which this is the identity map on E crossed with my other way of thinking about this predicate, which is going to be the adjoint. So, and then down here I've got evaluation. Okay, and then this bottom diagram commutes by definition of what this adjoint is. If you remember having my explicit map for the inverse transpose, that's literally exactly what this is.
You've been saying adjoint where you meant to say transpose.
Well, I meant to say transpose. It will end up being an adjoint, but at the moment it's not. Yeah, sure. Okay, I'll be more careful. If we look at the definition of the transpose, then that's exactly what this is saying. Okay, great. So we have that diagram commutes, and we have that diagram commutes. So what is the significance of this diagram commuting? Well, what this means is that if I have, let's look down here, if I have my predicate applied to my element, if that is the map true, if that is 1 into omega, if that is true, then that will be true if and only if going around the other way, which is evaluation at E of E crossed with my predicate. And so what this evaluation is saying is it's saying, does this predicate apply to E? Pretty cool, yeah?
Can I ask a dumb question?
Of course.
So the evaluation map, it's going from, if I think of it like in terms of sets, it's going from E times omega E, which is thinking of the sort of power set of E.
Yep,
So
absolutely.
is it basically just saying, well, pick an element of E and a subset of E, and either the elements in E in that subset or not?
Yep, that's exactly it. That's exactly how this works in the Toposes set. In fact, you've kind of underlined the next point that I'm going to make. So, okay. Which I actually think is one of the fun parts of this topos theory, is looking at familiar constructions and non-familiar topoi. But yeah, that's how it works in set. Awesome. So the next predicate that we're going to look at is the predicate is a singleton. Okay, so let's have a discussion about this. So, start with some object in my topos. Then this has a corresponding diagonal map. Better? Cool. So that's fine. Indeed, this is monic. And so the significance of it being monic is that it has a corresponding characteristic function. Okay, so think about the topos set for a second. This is going to map into 1 exactly when these two elements inside E are the same, right? So I have E1, E2, and it'll map it into 1 when E1 is equal to E2. Okay, so for that reason, that motivates the following syntax that I'm going to use. So I'm going to write delta E for this map, which is the Kronecker delta map. Okay, now this is a map into omega, and so I have a transpose for this.
You said Kronecker delta, but you want to justify that as set.
Yes, so it's coming from set again. Every time I say something like intuitively, we can think about this as, you can replace that sentence with in set it works as, and the sentence will still be true. So absolutely, in set this is literally the Kronecker delta map, so that inspires the notation that I'm using for an arbitrary topos. This admits a transpose which again, thinking about set, will send an element E in E to its singleton set containing it. Think about this as the power set. So for that reason, we notate this as this guy. By the way, just flagging this for those that don't have notes, this is obviously where all the notation is coming in. I'm going to be using these pretty extensively, so do you want a piece of paper? Oh, you're cool? Okay. So now there's a lemma here. This map is monic, as a matter of fact. It's not immediately obvious, but it is. I'll say a few words on the proof in a second. But the significance of this being monic is that, again, it itself has a corresponding characteristic map. Okay, great. So in set, what this does is it checks if what you have is a singleton set or not. Is a singleton. And then I just want to have a name for this map, so I'm not writing that everywhere. Sigma for singleton. Great. Okay, are there any questions about that? let's have a look at this lemma quickly. Okay, so this is another bunch of diagrams. Okay, so let E be in my topos and consider this guy. So this is the map I'm going to be showing is a monomorphism, which is going from E into omega to the E. And so consider having some morphism that's coming from some other object into E, then the following diagram, it's going to be a diagram here followed by commutes, and the diagram is this. So we have E up here, and we come down with the diagonal. And that's going like that. Now, I have this map coming into B, and sorry, let me have a look at this. Right, okay. So let's think about the diagram that is invisibly sitting here for a second. Then I have the diagonal on E, which I said that I had a characteristic function for, and I gave that a name, that was delta. Okay, and then that means that the following diagram must commute. Because if I rotate this by pi on 2, then I have exactly... No, wrong way. No, it's fine like this. Yeah, then I've got exactly the sub-objects classifier map. Okay, cool. So this is a pullback. So right square is just universal. Universal property of my sub-object classifier. This is in fact a pullback. Okay, cool. And then from here, I have a map from B to B, which is just the identity map, and also have from B to E, which is this map lowercase b. And so that gives me a map B cross E, which is this guy, right? Which is just the map induced by what I just said. And then this goes into here by B cross the identity on E. Okay, the left square, it's pretty believable that it commutes. In fact, it's also a pullback diagram. And this is essentially just an exercise in fiddling around with the product and universal maps corresponding to that. So I'm just going to write exercise. Okay, so what is the significance of having that both of these are pullback diagrams? Well, let me clear a board and then I'll tell you. Okay, so I'm trying to prove that this is monic, right? So I've told you what happens if I have 1b. So now let's say that there was a b dash that was going from b to e. Such that this guy after b is equal to this guy after b dash. Okay, well, if that was the case, then what I would actually have is the following diagram. So this guy is going from from omega, oh my goodness, sorry. This guy is going from e into omega to the e. Okay, so if I look at e going and then I want b cross e, so I want the identity on e. Okay. Sorry. Oh, great. Okay. Right, okay, so I'm trying to do a transpose argument. So I want to relate this map to its transpose. So what's going on is I actually have e cross e going into omega by the transpose of this map, which I've already told you is delta. Okay, so then what I actually have is going from e into omega to the e, which is the identity on e crossed with this map. Okay, and then I have the evaluation map on e. Okay, so I know that this diagram commutes. Now, what I have is this b, which is going from b into e. So I can extend this with 1 on e multiplied by b. Okay, and notice that if I had a b dash here, then I would also get commutativity of the diagram, because I know that this map is equal to the same map with a b dash replaced for a b. Okay, so what this tells us is that going from here down to here is actually the transpose of going from b followed by this Singleton set map. So, taking the transpose of this equation gives the following, that delta of e after 1e cross b is equal to delta of e after 1e cross b dash. Okay, and this is where I really wanted to get to. The reason why I wanted to get to this is because now I can look at the bottom line of this diagram that I drew up here, and I see that if I replace a b by a b dash, then I get the exact same map there. Okay, so let's look at the outermost square. We've got b1 omega b cross e. I've got these two maps from b cross e into omega. One with b, one with b dash. They're both exactly the same thing. What that means is that this wedge map 1b comma b is the same sub-object of the wedge map 1b cross comma b dash. So the upshot of all of this is 1b is a representative of the same sub-object as the one represented by 1 comma b dash. Okay, and the significance of this is if we recall what the equivalence relation is on sub-objects, it means that there exists an isomorphism that allows me to factor both of these sub-objects through each other, and so thus there exists H which goes from B isomorphically into B, such that 1BH is equal to 1B dash. Sorry? No, I don't want an H there, yeah. So I've made the choice to factor through this one. Then what this tells me is, it's really nifty. Now, if I project onto the first argument, that tells me that the isomorphism is in fact the identity isomorphism. And if I project onto the second component, then that will tell me that B is equal to B dash, proving that the set map is monic. Okay, so I got a little bit flustered in the middle of that. Does anyone want to ask any questions about that proof?
So did you use at some point that the outer square is a pullback diagram?
Yes. That is to say that the outer square is a pullback, and thus these two bottom maps that I mentioned correspond to the same sub-object, because if you remember what a sub-object is it's sub-monomorphism, which is such that there exists a unique map that turns the whole thing into a pullback. Mm-hmm. So I need a more to commute, I need it to actually be a pullback.
Right, great.
Yeah. So, and this is just actually the relationship between a map and its transpose. It's nothing more complicated than that. Okay. So, now, we can look at the third part of our talk, which is actually looking at the fact that elementary topoi are the same as topoi. Okay. So we can actually do lots of this before even writing anything down. So it's pretty clear that if you're a topos, you're an elementary topos. A topos looks much stronger than an elementary topos. So if we have all exponentials, then we do indeed have an adjoint to the fourth condition on an elementary topos, which is stronger than what we actually require for an elementary topos. And then all the other definitions are pretty much exactly the same thing. So for a Cartesian closed category, we have a terminal object and all binary products. And James mentioned in his talk that you can get all finite limits from that. And so therefore we have all finite limits. And from all finite limits, we can get all pullbacks as well. And so that means that we already have a sub-object classifier, because that was common in both definitions. So when I say what we have is starting from a topos going to an elementary topos, then we already have all finite limits, and so therefore we have the terminal object. We also have all pullbacks, and then the definition of a topos required that we have a sub-object classifier, so we definitely have that. And then a topos required that we have exponentials, which is a stronger condition than the fourth one. So that tells us that if it's a topos, then it's necessarily an elementary topos. Okay, cool. So that's a lot of the proof done already. Going back the other way, we can cut a lot of meat off it as well, because also, as James mentioned in his talk, if you have a terminal object and you also have all pullbacks, then that's actually enough to get you all finite limits. And so the fact that I required a terminal object and all pullbacks gave me all finite limits. Great. And then what do I need? I need a Cartesian closed category, so I need binary products, but I just told you I have all finite limits. James also mentions that binary products can be realized as a limit, a finite limit. Okay, good. Both conditions required a sub-object classifier, so now it actually remains to show that from my fourth condition, I can get all exponentials. That's actually what the meat of this proof is. So, with all that out of the way, it suffices okay, so it suffices to show that. And there's this kind of intuitive first step that you want to make to start understanding this. And I really want to do it all on one board, so I'm just going to clear this off.
Probably worth switching to normal rewriting at this point.
Maybe, yeah. It's still pretty messy, isn't it? Okay, so I'm not starting the proof yet. This is still just intuitive preamble. So consider the case when this is set. Okay, then let B be subset and let C be unset. So what I'm trying to give you is C to the power of B. So let's think about what that is. C to the B, we know that this is simply the set of all functions from B to C. Right? Now, this can be realized as a sub-object of the power set of B cross C. It's all the graphs. Okay, now this is a subset of the power set of B cross C, and so therefore it has a characteristic function. And this is going to go from omega B cross C into omega, which sends this to 1 if gamma is a graph, and 0 any other time. Okay, cool. Now I can be a bit more sophisticated with my language here, gamma is a graph, or I can be a bit more logical with it and actually write the definition. So let's get rid of that and say I send it to 1 if it's the case that for all B in the element of B, there exists a unique C in C such that BC is an element of gamma. Okay, think about that for a second. That's definitely saying that gamma is a graph. Okay, cool. So now I'm just going to work out, I'm edging towards saying this in an arbitrary topoi. So I just need to work out how to say this without looking inside elements. Now, there's actually a clever trick for dealing with the for all. And it goes like this. Consider the following function. which I'll call u. And this goes from omega b cross c into omega to the b, wait, something's wrong. Is that right? And then I'm going to say that gamma
Goes to B, goes to something. Whether or not this equals.
Don't I want to talk about membership next? Yes, I want to talk about membership first. Okay. Is that even true? No, it's not. No, this is correct. Okay, and that. Right, because then I'm going to talk about existence. Okay, so this is right. So this is going to get sent to a function which sends b into 1 if there exists a unique c in C such that bc is an element of gamma and it goes to 0 any other time. And then the idea, the clever part, is that gamma is a graph if and only if u of gamma is equal to the entirety of b. Right? Because let's think about what that says. If it is the case that this is the subobject b, it's for all b. That's the idea. Okay, great. So what that means is c to the b is the following pullback. Omega to the b, and I have 1 coming into this, which is just the transpose of that map that I mentioned earlier, which is true on b, because keep in mind I was just sending everything in b to 1. So I want to factor through that, which means I'm looking at b cross c. As long as that's u, then the pullback of this is going to be exactly c to the b. Okay. So now, all that I need to do is find a way of defining u in terms of an arbitrary topos, and then I found a way of defining the object for my exponentials. Okay, so just need u for an arbitrary topos. And this is what all of our work for predicates was done earlier. I can actually do this just using the language of is a singleton, etc. And so the way that I do that is, if I look at that, well, let's just look at membership to start off with. Now, as I mentioned, we have evaluation, and that's membership. So this has a transpose. So the transpose of the evaluation map from C cross B is the following. So I'm lifting C. And what this does is it sends B gamma to the function that sends C to 1 if BC is an element of gamma. And it sends it to 0 any other time. And so now to check that there exists a unique one, all I need to do is check that this sub-object is the singleton set. So I can just compose this with is a singleton. that will give this. Which is exactly what I said up there. The transpose of this, when I lift B across, is going to be exactly U. Is there anything you want me to refine?
Yeah, I mean, you're using the maps to thing. That final thing should be the image of the very left-hand thing, but you're sort of using it to denote the function, which is the second function, right?
Exactly. I don't know what to write here, so I'm looking at, I now want to compose this with the predicate is
Well,
a singleton.
it's one if there's a unique C.
Yeah, okay. Cool, good. And then the transpose of this is exactly U. Surely I would write down the exact same thing if I were to write it. Great. I'm getting a little nervous about time. I have a due at 3:15.
Oh, I see.
Yeah, and the I've got a friend that's covering the first little bit. The next bit so next bit is the evaluation map, which is a 5-piece community diagram. It's going to take a bit.
Yeah.
What do you reckon we do?
So basically define the array, right? Oh, yeah.
I haven't done the evaluation map. The evaluation map is.
Well, you probably have time to define it at least, right?
Let's write the
You
diagram.
can stop, I think.
Okay, yeah, I can do that. Yeah, let's do that.
It'll be faster with the arrays.
Cool. So the present point to make, oh, well, I haven't made any definitions yet. Okay, so now let's look at the proof. Let A be an elements from topos. Okay, then let B be my element which I'm trying to define an exponential for. So to define exponential, I need to give you a family of objects, which is indexed by objects in E. So let's C be some other one. Then let C to the B be, and I'm making a definition here. U is the transpose of sigma C. Remember that sigma is a singleton. Okay, cool. So I haven't given you an exponential yet. All I've given you is the family of objects. Then I need to give you a family of morphisms, which are the evaluation maps. And so what I need to say that if I'm in B cross C to the B, then I need a map from here into C. Now, thinking again about the topos set, then what this should really do is it sends B gamma to that unique C, which is such that BC is in gamma. And so what I can look at is I can then put that element inside the Singleton set, and then on this direction, just include this element into the power set of B cross C. And so it's, I don't know if it's big enough. What is this? This is going to be 1 on B cross M. I'm giving you M. M is that inclusion map. Well, M is that monomorphism. Okay, cool. And then here I have the evaluation. Okay, cool. And so let's remember what we're looking for. What I'm really looking for is a map from here into here, such that when I push along this diagram, push along this arrow, I get a commuting diagram for what I've just drawn. So what I need to do is construct a whole bunch of commuting diagrams and tell you that there must exist such a map. Okay, and the way that you do it is it's like this. We have this. That's sigma C. This is indeed a pullback, which we'll use, not just commuting. This is B cross omega to the B going in by evaluation on B, and then this one is 1B cross U. Sigma after ev C cross B is exactly this without the outermost corners, and so taking the inverse transpose, we have an explicit inverse transpose formula for that, which is exactly what commutativity of this diagram is saying. So this commutes, not a pullback. It commutes. And then we go that's true on B. This is the identity product with just the terminal map. And then this is actually the functor B cross blank applied to my definition of C to the B. So if you look at that and then apply the functor B cross blank, you get exactly that. So what do we have? Commutes. Commutes is a pullback. And then I actually have another one, which is this. And this one's actually the easiest one, but it looks really just good.
Well, there's a unique map to the terminal.
Yeah, but how do we know it commutes like that? Well, already, no, that's fine. Okay, I've drawn it even more distortedly, so let's not do that.
This is the definition of true B.
Exactly. So this is 1, and that's that. And then this along here is exactly, yes, terminal, and then followed by true. Yep, so that one's true B, and then this one is 1 cross the transpose of that. Sweet. So that bottom one commutes. Okay, and then it goes like this. I want to get a map from here to here. I told you that this one is a pullback. So in order to get that map, all I need to do is convince you that going along here is the same as going along here, because then by universal property of the pullback there must exist a unique one. I've already told you that all these diagrams commute, and so therefore I necessarily have that. Going bang, 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 is bang, 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 is bang, 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 is bang, 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 bang.
That was satisfying.
Absolutely. I saw like 15 minutes left and I was like, don't tell me I don't get to do it. And then that's going to be the evaluation map on, and then my notation is B and then C. Okay, and then the proof is still not done. You're then going to go, you think the nightmare's over, you're going to go and show that this is universal, which can be done. It's not beautiful, but it's not open. Okay, I think I've been up to doing the thing there, so.
That's great.
Alright, sweet.
Thank
you. Any questions? I do have 5.